From the outside, especially after companies became more secretive, it might feel like that AI progress has stalled. We barely see any attempt at disrupting the current AI stack. But behind the scenes, a lot of new breakthrough technologies are brewing up. Technologies that make current LLMs obsolete. We are talking about vastly more capable, more intelligent, faster, and more reliable AI models. In this video, I want to talk about 4 secret technologies out of the major labs leaked by researchers or by the companies themselves, but at a conceptual level, while the actual recipe is still hidden. By the end, you'll be left thinking, how fundamentally flawed are the current AI models, and how everything could literally change by any of these new technologies. First, infinite lifespan AI brewing on Google. A new architecture that lets you spawn a new AI into existence and keep it around as long as you want. You spawn a new instance of this AI and it starts to learn about your life, your projects. If it's not good as something that you care about, you just teach it. Give it tutorials, trainings, and examples. This AI can keep learning and adapting indefinitely. Today, the state-of-the-art attempt at building artificial general intelligence, AGI, is the transformer-based large language model. Transformer is highly effective at utilizing massive amounts of parallel compute. And that's the main reason it is so popular. But it has a well-known issue of limiting AI's lifespan in inference time. Basically, transformers are great at building the digital brain. But when it's time for that brain to actually operate in the real world, it can live for like minutes and dies out. Of course, since it is digital, you can run another copy of it. But you lose a lot of valuable information having to start over every time. On the consumer side, we see this short lifespan as the limited context window, and the digital copy as starting a new chat session. By the way, the lifespan is an analogy. The AI is limited by the number of tokens it can process, not by the actual time on the clock. Now, with this new architecture coming up, the AI can live forever with an infinite context window, and that's a real game changer. Listen to Jacob Bachman, the CEO of Manifest AI, revealing this new class of architectures.
The writing is on the wall for me as somebody working in this space. Transformers do not have a lot of time left as the dominant architecture. By the end of 2025, this year, every hyperscaler will at the very least be working on a sub-quadratic foundation model. By the end of next year, nobody will be using transformer models, or almost nobody. It's a bit ridiculous that we have 2 ways of giving data to the model to govern the response we're going to get out of it, and we're putting 1 billion times more data into one of them. Why would we be doing that? We get very concrete and well-understood benefits. This is what you call a context scaling curve, or context-wise loss curve. It basically shows that as you give the model more and more tokens of context, its predictions improve. In this case, just measuring the negative log likelihood, the loss, and meaningfully, right? The gap between these 2 lines, which are models at very different scales, is not as large as the gap between the end of one line when you've given it a lot of context and the beginning of that same line.
So what makes transformers so limited, and how this new architecture fixes that? As you probably know, transformers are next token predictors. You give them some amount of text and they predict the next token, let's say word. But then how do they keep a conversation one word at a time? The trick is, and this is what made ChatGPT such a huge success, you fine-tune the model on a lot of user/assistant turn-based conversations. And you put some sort of a special character at the end of the assistant turn, let's say EOT. The AI learns that at the end of each assistant turn, there should be this special character. So you keep feeding back text to the model, and the model produces 1 token at a time until you see that special character. Then you know the assistant turn is over. So you wait for the user to type again, you take all of that text, including all the previous interactions, you feed it back to the model gives you another token, and so on. So although it might seem like you are having a conversation with the AI 1 message at a time, this machine has no concept of the loop or any sort of memory. It just receives a giant wall of text and predicts the next token. If the conversation keeps moving, the AI has to process a bigger and bigger wall of text. And transformers are especially awful at that, because transformers attend to the relation of every word to every other word, including itself. That's n times n, an operation that explodes quadratically as the number of words grows linearly. So it's not a question of more compute, there is just actually no hope to keep up on longer horizons. So what's the fix? If you look closer, the whole issue is just memory. What should be remembered, what should be forgotten, and when. The transformer basically has the worst solution of all. Just remember everything always. But there is a class of architectures called Sub-Quadratic that include memory as part of the main system, not just as an add-on. Google showed us a glimpse of their work a couple of months back called Titans, Learning to Memorize at Test Time. Titans showed that the model can be more selective about what it keeps by using a surprise mechanism. So they taught the model to memorize unexpected things, and it was able to become more effective than transformers on common sense reasoning, genomics, and time series tasks. Using 3 layers of short, long, and meta memory systems, they trained the model to hold information much more effectively and comfortably beat transformers on longer context windows while being more efficient. While Titans is a nice glimpse, and we could suspect that Google used some of the same ideas to push Gemini's context window to 1 million, there are a number of competing ideas in all major labs trying to replace a transformer with a more integrated memory system, and any of them could change the game entirely. The second technology shows that as much as everyone loves to say that Turing test is done, AI never actually passed it. There is a simple test you can run and find a hole every time. We'll talk about the test, but let's see why the hole exists first. Right now, neural network seems so blindingly obvious. Just copy the brain with neurons and parameters and weights. But for decades, it was considered a fringe idea. And one of the main people who championed it during that time is now saying he has moved on from LLMs. Yann LeCun, which alongside Geoffrey Hinton and Yoshua Bengio is considered one of the godfathers of modern AI, said this.
But I tell you one thing, which may surprise a few of you. I'm not so interested in LLMs anymore. You know, the last thing, they are in the hands of, industry product people, improving at the margin. And so the type of architectures that I think we need for systems that really can deal with the real world is completely different from the ones that we deal with at the moment.
He is working on a new architecture that addresses 2 fundamental problems with current AI models. The first one might sound like a feature, but Yann considers it to be a bug, or at least a very good sign that we are doing something fundamentally wrong. When you are talking to ChatGPT, for example, what is the one thing that is in stark contrast with any human on the planet? The AI somehow knows everything. It has memorized the entire internet. And that's just impossible for any human. If the guy on the other side knows everything, it is an AI. It's that simple. Why that might be a bug? Conceptually, the AI is mimicking the brain. Brain is a gigantic network of billions of interconnected neurons, and everything we know and understand is stored on these connections called the synapse. Theoretically, there is a limit to how much information could be stored on these connections. The bigger the network, the more information, heuristics, and patterns could be stored on them. Now, the amazing part is that the biggest AI models today have around 2 trillion parameters. And parameters are digital equivalent of synapses in the brain. A normal brain has 10 to 100 times more connections, not taking into account that synapses are analog and probably hold more information than a 32-bit floating point parameter. But a human can't possibly remember just 100 books, let alone the entire internet. Yann LeCun's idea is that maybe we are wasting too many parameters on the exact words, not having enough space to store patterns. Connections wasted on an exact word is taken away from a higher level abstraction opportunity. It's like the difference between the student who memorizes all the answers and the one who doesn't remember the exact words but understands the subject. Memorizing words doesn't generalize enough, and maybe that's why we don't have AGI yet. Interpretability studies of current AI actually show models are under-parameterized.
All of the interpretability work on superposition states that the models are always under-parameterized, and they're being forced to cram as much information as they possibly can. And so if you don't have enough parameters, and you're rewarding the model just for imitating certain behaviors, then it's less likely to have the space to form these very deep, broader generalizations.
The second problem is thinking and planning. There are reasoning or thinking models out there, but they are a cartoon version of what actual thinking and planning looks like. You remember how we made the model conversational, you fine-tune the model to output in the user/assistant format. And now to make the model think, you add another section and call it thinking. So on the user side, it seems like thinking is this different process that the model is going through. But in reality, it's again just part of this giant wall of text. That's not to say it doesn't work. It obviously forces the model to spend more compute on a problem. And also you have the opportunity to reinforce logical thinking in this area, using a lot of math and coding problems, which helps the model to reach better solutions. But the model is not actually thinking, it is talking out loud to itself, which is a very slow, inefficient, and inaccurate process. What's the alternative? Giving the model the ability to think in the space of ideas. In a transformer, when you feed text to the model, the first layer is just a learned lookup table, turning each word into a vector. Vectors are essentially representation of ideas or concepts. Internally, transformer models cultivate an understanding of concepts within incredibly rich, high-dimensional vector spaces. However, the final output layer has to distill this complex, continuous representation into a discrete choice from a limited vocabulary. This projection from a vast internal conceptual space to a finite set of words invariably leads to loss of some of the original semantics. Now think about a model that is able to think in the space of ideas for minutes, not having to project ideas to words, but manipulating vectors until it reaches a conclusion. Then it starts outputting words. Funny enough, for the same reasons the original neural network was dismissed, this new approach isn't popular yet. The thought process in vector space is not readable, and researchers want to know what the model is thinking about. Even in the original DeepSeek R10 paper, although the model was forced to project its thoughts into tokens, it tried to at least invent a more efficient language for its thinking process, mixing languages and using weird symbols. But the researchers fine-tuned the model to have readable thoughts, even though it actually hurt the performance. If the model thinks in the space of ideas for minutes, it's very hard to keep it grounded and make sure it gets enough rewards in a reasonable timeline. More open-ended means potentially more powerful, but more difficult to guide. There are competing ideas in different labs on this frontier, but Jan LeCun's architecture is called Joint Embedding Predictive Architecture, or JEPA. This is a setup that pushes the models to predict the features and semantic representations rather than the detailed output. For example, in image JEPA, the model tries to predict the abstract representation of the missing patch instead of the raw pixels. It's a bit complicated how it works, but I try my best. Imagine three friends playing a game: Charlie, Penny, and Terry. Charlie gets a picture with a missing part, and he describes it to Penny. It's a blue sky with fluffy white thingies, and the right corner is missing. Penny never sees the picture, but she has to guess based on Charlie's description what might be in that missing area. She says, "I guess there is a black sedan in that missing corner." But then Terry gets the whole picture. He looks at it and says, "Nope, it's actually more sky and white fluffy thingies." So both Charlie and Penny learn when it's a blue sky with fluffy thingies, there is a possibility that the missing corner is the same thing. When there is cat ear, there is likely a cat nose as well. When there is a sky, there might be a bird, and so on. And over a lot of training rounds, Charlie learns to understand conceptual representations without ever having to predict the actual pixel. In reality, Charlie and Terry, the first and the third guy, are actually the same model, but Terry's weights move slower. So Charlie and Penny have a more stable target to aim for. Also, crucially, there is no describing in words. It's all vector embeddings, encoding very rich representations of the image. There is actually a possibility that these very successful video models like Veo and Sora are using the same ideas behind the scenes. How does this help with thinking though? The model can work with those vectors and go back and forth in the space of ideas and only output words when it's ready to talk. Of course, it's easier said than done, and there are a lot of engineering and feasibility challenges, especially in scale. But the ideas themselves are serious leaps over the current AI, and every lab is working on them. No matter which ideas win though, one constant remains. These more capable and more open-ended models are invariably more data hungry, and internet is running out of juice. So the next frontier is synthetic data. Synthetic data might sound like, hey, O3, give me a data set to train this new model. Yes, that's one way to do it, but there are more efficient and effective ways. If done tastefully, synthetic data is actually far above and beyond real data in improving model performance. AlphaGo and AlphaZero started with some real data, And then they blew up in capability with self-play, which is a form of synthetic data generation. The reason we hear self-improving AI every other day now is exactly this. An efficient self-play environment has very significant upsides, although there are some misconceptions about how a self-improving AI will automatically yield God itself. The truth is, all of these AI models can self-improve in a very narrow dimension. It's very hard to define the correct goals and rules for a general system to achieve recursive self-improvement. I don't think it's even solved conceptually, let alone being engineered. But one of the more promising ones that I thought deserved a spot in this video was Absolute Zero from China. The biggest jump in AI capabilities after ChatGPT came out of reasoning models. And as we touched on them briefly, the reasoning models are fine-tuned to output in the specific format of think, then response. And then they are trained to have better reasoning in this area using reinforcement learning. To make sure the reasoning steps in this area are effective, you have to have a data set of challenging problems with verifiable answers. You give the model the problem, you don't tell it how to think, you just care about the final solution. So the model, over time, develops its own strategies to reach the final answer. Coming up with a data set, though, isn't trivial. Expert humans have to manually produce them, but Absolute Zero has a brilliant way of getting around that. We propose Absolute Zero, a new paradigm of reasoning models in which the model simultaneously learns to define tasks that maximize learnability and solve them effectively, enabling self-evolution through self-play without relying on external data. This is a much more scalable solution for training reasoning models. The system not only gets better at solving problems, but it gets better at proposing problems as well. And this system, without any data, outperforms models of its own size, even the ones trained for a specific task. Does this scale to infinity? No, because there is a limit on verifiable problems. And the time horizon is limited. We are not talking about tasks that might require several days of thinking. We are talking about several minutes, at least for now. Now we get to the last secret technology that Demis Hassabis literally introduced in the middle of Google I/O. And everyone somehow missed it. He actually was expecting a big round of applause. And no one seemed to realize what he just introduced. Why people didn't get it, we need a bit more context. There is a mismatch between how OpenAI and Google DeepMind view AGI, and that difference in philosophy might show sooner than later. OpenAI defines artificial general intelligence as a highly autonomous system that outperforms humans at most economically valuable work. This definition is based on a financial threshold of $100 billion in profit, a benchmark likely used in OpenAI's agreement with Microsoft. So, to OpenAI, AGI is any autonomous system that can outperform humans in economic activities. It doesn't have to be better or even on par with humans in everything. And here is how Demis Hassabis of Google DeepMind defines AGI.
What I'm interested in, and what I would call AGI, is really a more theoretical construct, which is what is the human brain as an architecture able to do, right? And that's, the human brain's an important reference point because it's the only evidence we have maybe in the universe that general intelligence is possible. And there, it would have to be able to, you would have to show your system was capable of doing the range of things even the best humans in history were able to do with the same brain architecture. It's not one brain, but the same brain architecture. So what Einstein did, what Mozart was able to do, what Marie Curie, and so on. And that, it's clear to me today's systems don't have that. And then the other thing that why I think it's sort of overblown the hype today on AGI is that our systems are not consistent enough to be considered to be fully general yet. For me, for something to be called AGI, it would need to be consistent, much more consistent across the board than it is today. It should take like a couple of months for maybe a team of experts to find a hole in it, an obvious hole in it. Whereas, today it takes an individual minutes to find that.
Now the natural question is, how does the brain work as an architecture? When I first learned this, I was blown away for days. Brain is one giant neural network that takes all sorts of sensory input, mainly vision, hearing, smell, taste, and touch, and outputs all sorts of actions. But what a lot of people might not realize is that the brain doesn't freaking care. It just takes any sort of input and figures out what to do with it. If you connect a new sensor to the brain, it just learns to make sense of it. Listen to Dr. Eagleman from my favorite TED Talk of all time.
There are hundreds of thousands of people walking around with artificial hearing and artificial vision. So the way this works is you take a microphone and you digitize a signal and you put an electrode strip directly into the inner ear. Or with the retinal implant, you take a camera and you digitize the signal and then you plug an electrode grid directly into the optic nerve. These technologies speak the language of Silicon Valley, and it's not exactly the same dialect as our natural biological sense organs. But the fact is that it works. The brain figures out how to use the signals just fine.
Isn't it insane that we can just connect an electrode grid to the optic nerve and the brain starts to make sense of it? Just a new, completely foreign digital signal from a camera. No drivers, no patches, no ports, and the brain is like, hey, welcome, you are my new eye now.
And this is a very efficient kind of machine. It's essentially a general purpose computing device, and it just takes in everything and figures out what it's going to do with it. And that, I think, frees up Mother Nature to tinker around with different sorts of input channels. So I call this the pH model of evolution. And I don't want to get too technical here, but pH stands for potato head. And I use this name to emphasize that all these sensors that we know and love, like our eyes and our ears and our fingertips, these are merely peripheral plug-and-play devices. You stick them in and you're good to go. The brain figures out what to do with the data that comes in.
And they use this knowledge to help blind people to see through their tongue.
And this is a little electrode grid that sits on your tongue. And the video feed gets turned into these little electrotactile signals. And blind people get so good at using this that they can throw a ball into a basket, or they can navigate complex obstacle courses. They can come to see through their tongue. Now that sounds completely insane, right? But remember, all vision ever is electrochemical signals coursing around in your brain. Your brain doesn't know where the signals come from, it just figures out what to do with them.
The same thing on the output side. For example, with Neuralink, the brain just learns to use the electrodes connected to the neurons and sends signals to move the cursor on a screen. So the brain as an architecture is not a text model, it's not an image or a video model, it's an anything model. That's the point when Demis introduces a word model. An AI that is not dominated by one form of input, text or image or anything, but it learns from all of these different modalities, video, image, text, sound, anything. And it internally builds a rich representation of the word that is independent of the nature of the input. I think no one explains it better than Jan LeCun himself.
So a lot of people are working on world models, right? So what is a world model? A world model is, we all have world models in our mind. This is what allows us to kind of, manipulate thoughts, essentially. So, we have a model of the current world. You know that if I push on this bottle here from the top, it's probably going to flip, but if I push on it at the bottom, it's going to slide. And, if I press on it too hard, it might pop. So we have models of the physical world that we acquire in the first few months of life. And that's what allows us to deal with the real world. And it's much more difficult to deal with the real world than to deal with language.
Multimodal AI models are an attempt, but a true word model is much more ambitious and powerful. And that, as Demis Hassabis said himself, is the ultimate goal and the vision of Gemini. Of course, Google DeepMind didn't let us in on the specifics of the technology, but most definitely, they are combining a bit of everything we talked about today. When we look at the news, we see the AI that works, makes real products, and is mature now. But all the interesting stuff are happening in this area. Scientific challenges and solutions that aren't bound to product deadlines. You remember this guy leaving to build ASI in one shot? That's what he was talking about. Just a relentless pursuit of addressing the real game changers. It seems like we have at least a couple of obvious leaps in sight. That's it for this video. I hope you enjoyed it as much as I enjoyed making it. Thanks for watching. See you in the next one.